6 in the morning, July 8, 1944, a field outside Saint-Monvier-Nord in Normandy, 6 kilometers west of Caen. A heavy mist is rising off the wheat. The temperature is just above 60 degrees Fahrenheit. Sergeant Earl Thornton of the 2nd Armored Division, 67th Armored Regiment, climbs out of the driver's hatch of an M4A3 Sherman tank named Carolina Belle and stands in the long, damp grass looking at his tank. There is a hole in the rear engine deck. The hole is approximately the size of a basketball. It was made the previous afternoon by a 75mm armor-piercing round from a German Panzer IV, fired at 500 yards as Carolina Belle was repositioning behind a hedgerow. The round did not penetrate the crew compartment. It hit the engine instead. The Ford GAA V8 inside is destroyed. The connecting rods on cylinders 3 and 7 are bent. The crankshaft is fractured. Oil is pooling in the engine bay. The tank is, by every definition that mattered to a tank crew in 1944, a write-off. Except that it is not a write-off, and by 10 o'clock that morning, Carolina Belle will be running again. Not running in the sense that someone will have patched the existing engine. Running in the sense that the entire Ford GAA, with its complex casting and its bent rods and its fractured crankshaft, will have been physically lifted out of the hull as a complete unit and replaced with another Ford GAA, brand new, still wearing its olive drab depot paint, drawn from a stack of crated engines on a flatbed truck at the forward echelon maintenance section of the 17th Ordnance Battalion. 4 mechanics from the 17th Ordnance will do the work. They will use a single M32 tank recovery vehicle equipped with a 30-ton hoist, a torque wrench, a set of metric and SAE sockets, and a printed technical manual that tells them exactly which bolts to undo in what sequence. Total elapsed time from arrival on site to engine running on the new power plant will be approximately 4 hours and 40 minutes. By noon, Carolina Belle will be back in the regimental motor pool. By the next morning, she will be back in combat. 70 kilometers east, the same morning, a captured American Sherman tank is sitting in the courtyard of a farmhouse near Falaise that has been requisitioned by the Wehrmacht. The tank had been abandoned by its crew during the fighting around Caen on July 2nd, set fire by its own driver as German infantry closed in, but the engine compartment had been only partially burned. The Germans towed it back to the courtyard for inspection. The mechanic, now standing next to it, is Feldwebel Hans Müller of the 12th SS Panzer Division Hitlerjugend. He has been a tank mechanic since 1940. He has serviced Panzer IIIs, Panzer IVs, Panthers, and 1 Tiger. He understands what tank maintenance looks like in a German army workshop. He is standing next to the Sherman with the rear deck hatches open, and he is trying to work out what he is looking at. What he is looking at is a Ford GAA V8 engine sitting inside a steel cradle that bolts to the hull at 6 points. 8 quick disconnect electrical connectors run from the cradle to the rest of the tank. 4 fuel and coolant lines connect through standardized fittings that he immediately recognizes as the kind of self-sealing couplings that aircraft mechanics use on aviation engines. The drive shaft to the transmission disconnects through a splined coupling held in by a single removable pin. The entire engine, in other words, is designed to be lifted out of the tank as a single unit and replaced by another. Müller has never seen anything like it. The Maybach HL230 in a Panther is bolted into the hull through dozens of separate mounting points. Its fuel and coolant lines are individually threaded. Its electrical wiring runs in a complex harness that has to be disassembled connection by connection. Replacing a Maybach HL230 in field conditions, when it can be done at all, takes between 2 and 3 full working days for an experienced crew, and frequently requires the tank to be returned to a depot facility well behind the lines. Müller, looking at the Sherman, understands immediately that the Americans have designed something his army has not designed and has not even attempted. He notes the design carefully in his report. The report goes up the German chain of command. The information is recognized as significant.
nothing is done about it. By July of 1944, it is far too late for the Wehrmacht to redesign the Panther's engine mounting system.
This is the paradox at the center of Allied armored warfare in the European theater of the Second World War, and it is the paradox that German tank designers and German tank maintenance personnel found most difficult to accept. The American Sherman tank was, in almost every individual measure of tactical capability, inferior to its German contemporaries. Its gun was less powerful than the Panther's long 75mm. Its frontal armor was thinner and less effectively sloped than the Panther's. Its silhouette was higher than the Panther's. Its optics were not as good as the German Zeiss sights. By the standards of a single, one-on-one engagement, the Sherman lost more often than it won when it met a Panther head-on. The German tank crews and tank designers knew this. They drew confidence from it. What they did not appreciate, and what cost them the campaign, was that the Sherman was designed for a different kind of war. The Sherman was designed to be repaired. It was designed to absorb damage and return to service. It was designed so that its engine could be replaced in a wheat field by a 4-man maintenance team in less than half a day. It was designed so that the tank crew, the maintenance battalion, the supply depot, and the factory back in Detroit were all part of a single integrated system that kept Shermans running through a campaign that destroyed thousands of them. The Panther was designed to win individual battles. The Sherman was designed to win the campaign. The German mechanic looking at a captured Sherman in a Norman farmyard in July of 1944 was looking at the visible expression of a design philosophy that his country had not adopted, and that, by the time he reported what he had seen, his country no longer had the industrial flexibility to adopt. The popular history of the Sherman tank focuses on the tank as a fighting machine. It compares the Sherman's 75mm gun against the Panther's 75mm gun. It compares the Sherman's armor against the Tiger's armor. It tells stories of individual tank duels, of brave crews, of officers who modified their tanks in the field to mount the better British 17-pounder gun. These are real stories. They matter. But they miss the central engineering fact of the Sherman, which is that it was not really designed as a fighting machine. It was designed as a fighting machine that could be returned to combat after being hit, after being broken, after being immobilized, after being abandoned, after being recovered, faster than any tank in any other army anywhere in the world. The men who designed this capability were not famous. They worked in the Ordnance Department of the United States Army in offices in Washington and Detroit and Aberdeen, Maryland. They wrote technical manuals. They specified torque sequences. They standardized fasteners across 9 different American tank engine programs. They negotiated with General Motors, Ford, Chrysler, Continental Motors, and Caterpillar to get those companies to design tank engines that could be installed and removed using a common set of tools and procedures. They built the M32 tank recovery vehicle, a Sherman chassis fitted with a 30-ton boom and a 60,000-pound winch capable of pulling a disabled Sherman off a battlefield and onto a flatbed in under 30 minutes. They built the doctrine. They built the depots. They built the spare parts pipeline. None of them are in the popular histories. All of them won the campaign. The central engineering concept the Ordnance Department imposed on every American tank engine program after 1941 was something called the power pack. The idea was simple. The engine, the cooling system, the fan drive, the oil reservoir, the air filters, the starter motor, the generator, the carburetors or fuel injection pumps, the ignition magnetos, and the necessary auxiliary plumbing would all be assembled at the factory as a single integrated unit, mounted on a steel cradle that defined the unit's mechanical interface with the tank hull. The power pack would be tested as a unit, shipped as a unit, installed as a unit, removed as a unit, and overhauled as a unit. The tank in this conception was a hull and a turret and a power pack receptacle. Whatever power pack the supply system delivered, the tank could accept. Whatever power pack failed in the field, the supply system could replace. The Continental R975 radial engine that powered the M4 and M4A1 Sherman variants was the first American tank engine to be designed around the power pack concept, though incompletely. The Ford GAA V8 that powered the M4A3 was a fully realized power pack from the moment it entered production. The General Motors 6046 twin diesel that powered the M4A2, the Chrysler A57 multibank that powered the M4A4, and the Caterpillar D200A that powered the M4A6 were all designed to fit into the same hull, mate to the same transmission, draw from the same fuel system, and operate within the same cooling architecture. The mounting bolt patterns were standardized, the driveshaft splines were standardized, the electrical connectors were standardized. A Sherman maintenance crew that had been trained on a Ford GAA could remove a damaged Ford GAA and install instead a Continental R975 or a GM 6046 or any of the other engines in the inventory. The man who imposed this discipline on the American tank industry was Major General Levin H. Campbell, Jr., who served as Chief of Ordnance from June 1942 through the end of the war. Campbell had been a career ordnance officer since 1909. He had spent his career thinking about the relationship between weapons design, production capacity, and field maintenance. When he took over the Ordnance Department in the middle of 1942, the American tank program was still in chaos. Different manufacturers were producing tanks with different engines, different transmissions, different electrical systems, all without coordinated technical standards. Campbell, working with his Director of Research and Development, Major General Gladian M. Barnes, instituted a program that they called interchangeability. Every component on every tank in every variant would be designed to a common technical specification. Different manufacturers could produce different versions, but the versions had to fit together. The Ford GAA produced at Ford's Highland Park plant had to be physically interchangeable with the Ford GAA produced at the Lima Locomotive Works subcontract facility. The transmission produced by Detroit Tank Arsenal had to be physically interchangeable with the transmission produced by Pacific Car and Foundry in Renton, Washington. This was, in 1942, a radical and difficult idea. American manufacturing had grown out of 19th-century traditions in which each company designed its own components and protected them as proprietary advantages. Campbell and Barnes forced the industry to adopt a different model. The component drawings, the dimensional tolerances, the material specifications, the fastener standards, all of them became Army property, shared across every contractor in the program. A spare part manufactured in Detroit had to fit a tank built in Lima. A spare engine cast in Cleveland had to bolt into a hull welded in Renton. The contractors initially resisted. Campbell did not yield. By the middle of 1943, the resistance had collapsed. The system worked. The cost of the system, paid in surrendered industrial autonomy, was paid back many times over by what the system delivered on the battlefields of Europe. The first Sherman engine, the Continental R975 radial, was an interesting case because it was not originally designed as a tank engine at all. It was an aircraft engine, the 9-cylinder Wright R975 Whirlwind, which had been used in biplanes throughout the 1920s and 1930s. Continental Motors had licensed the design from Wright Aeronautical and built it under contract for the Army's M3 Lee medium tank, which entered production in 1941. When the Sherman replaced the Lee in 1942, Continental refined the R975 with stronger bearings, better cooling, and a downdraft carburetor optimized for ground operation rather than for high-altitude flight. By 1943, Continental had built more than 53,000 R975 engines for American tanks, M3 Lees, M4 Shermans, and M18 Hellcat tank destroyers. The R975 was not an ideal tank engine. Its 9 cylinders, arranged in a radial pattern like the petals of a flower, made the engine wide and tall. It required a massive cooling fan to force air across the cylinder fins because the radial layout that worked beautifully in a moving airplane did not work well in an enclosed tank engine compartment. It burned aviation-grade gasoline, which was volatile. It produced 350 horsepower from a displacement of 1,510 cubic inches, which was less power per liter than the Ford GAA or the GM 6046 would achieve. But the R975 had one critical advantage. It had been designed as a removable unit from the start. The R-975 in a Sherman could be lifted out of the hull, complete with its cooling fan and shroud, in approximately 3 hours by an experienced 4-man maintenance crew. Continental shipped replacement R-975s to forward depots in wooden crates with all auxiliary equipment attached, painted, tested, and ready to install. The reason the Sherman ended up with 5 different engine options was not because the Ordnance Department wanted variety. It was because Continental Motors alone could not produce enough R-975s to meet the demand for medium tanks once American production scaled up in 1942. The Army Air Forces also needed R-975s for trainer aircraft. The competition for engines was fierce. To solve the bottleneck, the Ordnance Department turned to the only industry in America that had the engineering talent and the manufacturing capacity to produce tank engines at the scale the war required, which was the automobile industry. General Motors offered the 6046, 2 GM 671 inline diesel bus engines bolted together side by side. Ford offered the GAA, an 1,100 cubic inch V8 derived from a pre-war aircraft V12 program. Chrysler offered the A57, 5 Chrysler L-head 6-cylinder car engines arranged in a radial pattern around a central gearbox. Caterpillar offered the D200A, a 9-cylinder radial diesel derived from a Wright aeronautical aircraft design. Each of these engines produced approximately the right amount of horsepower for a Sherman. Each had different mechanical characteristics. The GM 6046 was a diesel, which meant it was less prone to catching fire when the tank was hit. The Ford GAA was a smooth-running V8 that the Army eventually selected as its preferred engine. The Chrysler A57 was complicated to maintain but easy to manufacture from existing automobile parts inventories. The Caterpillar D200A was rugged and fuel-efficient, but went into only a small number of M4A6 tanks. The Ordnance Department accepted all of them because all of them met the interchangeability standard. Any Sherman hull could accept any of these power packs with appropriate adapter kits and minor wiring modifications. The factories could ship tanks with whatever engine was available. The depot system could swap engines if necessary. The unit in the field could fight the war. The element that made the Power Pack concept work in practice, more than any other single technical decision, was the standardization of quick disconnect fittings throughout the engine compartment. The Ordnance Department adopted, for all American tank engines after 1942, the SAE J514 series of self-sealing hydraulic and fuel line couplings. These had been developed in the 1930s by the Society of Automotive Engineers in cooperation with the aircraft industry, primarily for use on hydraulic landing gear systems. They were precision-machined steel fittings with internal springs and rubber seals that allowed 2 fluid lines to be coupled or disconnected without any leakage, without any tools, in a matter of seconds. Push the 2 halves together, twist the locking collar, the connection was made. Twist the collar back, pull the halves apart, the connection was broken and both lines self-sealed. Every fuel line, every coolant line, every oil line, every hydraulic line on every American tank engine after 1942 used these fittings. The electrical connectors followed a similar standardization, using the AN series military aircraft connectors that allowed a single twist and pull operation to disconnect dozens of wires simultaneously. A mechanic preparing to remove a Ford GAA from a Sherman hull did not have to drain any fluid system, did not have to undo any threaded fittings, did not have to trace any individual wire. He simply disconnected the quick disconnect couplings, undid the mounting bolts, and the entire engine assembly came out as a clean unit. The Maybach HL230 in a Panther required threaded fittings on every fluid line, individually unbolted electrical terminals on every wire, and complete drainage of the cooling system before the engine could be lifted. The time difference between the 2 procedures was not marginal, it was on the order of an entire working day. The other piece of equipment that made Sherman field maintenance possible at the speed it operated was the M32 tank recovery vehicle. The M32 was a Sherman with its turret removed and replaced by a fixed cylindrical superstructure carrying a 30-ton A-frame boom that could be raised, lowered, and traversed by hydraulic controls. Inside the superstructure was a 60,000-pound capacity winch driven off the M32's main engine. On the rear deck, a set of welding equipment, oxyacetylene torches, an air compressor, a 40-gallon hydraulic fluid reservoir, and stowage for tools sufficient to perform every field-level maintenance operation on a Sherman. The M32 carried a crew of 4, a driver, a winch operator, and 2 mechanics. It moved with the combat units. It worked where the tanks worked. When a Sherman was disabled in combat, the M32 came forward. The boom lifted the disabled tank's rear engine deck plate. The winch pulled the damaged engine out of the hull and lowered it onto a flatbed waiting on the road behind. The boom then lifted a replacement engine off the flatbed, lowered it into the hull, and the mechanics made the connections. The winch and boom together could also drag a completely disabled tank off the battlefield, hoist it onto a tank transporter, and return it to a rear depot for more extensive repair. The American Ordnance Department built more than 1,600 M32 tank recovery vehicles during the war. Every American armored battalion had one. Every German panzer division had nothing equivalent. The German Bears Panther recovery vehicle, derived from the Panther chassis, was produced in such small numbers, only 347 were built, that most German armored units did not have one. When a Panther was disabled, it had to be towed by another Panther, an inefficient process that often disabled the second tank as well, or it had to be abandoned. The American Army organized its tank maintenance around a 4-echelon system that flowed work from the field to the rear depots in a structured way. First echelon maintenance was performed by the tank crew itself. Daily checks, lubrication, minor adjustments, refueling. The crew did this work using the tools stored in the tank's external bins and was expected to be self-sufficient for routine operations. Second echelon maintenance was performed by the maintenance section attached to each tank company. These were mechanics who traveled with the combat units in light trucks and could handle moderate repairs, tire changes, track repairs, minor engine adjustments. Third echelon maintenance was the Ordnance Battalion, the unit that performed major component replacements like engine swaps, transmission changes, and complete cooling system overhauls. Each U.S. Armored Division had an Organic Ordnance Maintenance Battalion of approximately 700 men, organized into mobile maintenance companies that could reach any tank in the division within hours. Fourth echelon maintenance was the rear depot, located typically 100 or more kilometers behind the front line. The depots performed complete tank overhauls, rebuilding engines, machining new parts, replacing armor plates. Disabled tanks that could not be repaired in the field were sent to the depots by tank transporter. Depots in Normandy in 1944, then in Belgium, then in Germany, processed hundreds of disabled tanks per week, returning many of them to combat-ready condition within 7 to 10 days. The depots themselves were extraordinary operations. The depot at Saint-Lô, established in August 1944, employed over 3,000 mechanics. The depot at Liège, established in October, employed over 4,000. These were not French or Belgian civilian workshops. These were American Army organizations with American mechanics using American tools and American spare parts, set up in former German military facilities or in commandeered factories, working around the clock to rebuild damaged American armored vehicles. They were the rear half of the system that allowed Sherman engines to be replaced in hours rather than weeks. The German army had a maintenance system as well, but it was organized differently and worked far less effectively. German tank maintenance was organized around 2 principles that worked well in peacetime and very poorly in wartime. The first principle was high-precision craft. German tank mechanics were trained as fine machinists, capable of hand-fitting parts within tight tolerances. The training program was excellent. The output was outstanding when individual mechanics had the time and the materials to do their work properly. But the training took years, and the materials were expensive, and the time was not available. The second principle was centralization. Major repairs on German tanks were performed at large central facilities, the most important of which were the original manufacturer's plants. A Panther that needed a serious overhaul was, in many cases, returned by rail to the MAN factory at Augsburg, or to the Henschel works at Kassel, or to the Daimler-Benz facility at Berlin-Marienfelde,
repaired there over a period of weeks, and returned to the front. The German army did not have an equivalent to the American Mobile Ordnance Battalion with the M32 tank recovery vehicle and the boxes of crated spare power packs. This centralization meant that German tank maintenance was efficient in absolute terms when it could be performed at all, but it was completely vulnerable to disruption. When the Allied bombing campaign destroyed the Augsburg factory in March of 1944, the central facility for Panther overhaul was eliminated. When Soviet armies advanced into eastern Germany in early 1945, the rail network that moved damaged tanks back to factories collapsed. The German maintenance system, which had been designed around the assumption of secure rail communications to a few central repair points, could not adapt to a war in which those communications no longer existed and the central points themselves were under bombardment. Disabled Panthers piled up in field assembly areas with no way to repair them. They were eventually destroyed, scrapped, or simply abandoned. The Maybach HL-230, when it failed, killed the tank in a way that the Ford GAA, when it failed, did not.
A Sherman engine swap in field conditions, performed by a competent Ordnance Maintenance Battalion crew on an M4A3 with a Ford GAA power plant, followed a sequence that had been rationalized through dozens of training exercises and hundreds of actual combat operations. The crew arrived on site with the M32 tank recovery vehicle and a flatbed truck carrying the replacement engine. The mechanics opened the tank's rear engine deck, which consisted of 4 armored hatches secured by quick-release latches. They removed the air cleaners, which lifted out as complete units after disconnecting 2 clamps. They drained the cooling system into portable containers for reuse. They disconnected the 8 electrical quick-connect terminals on the engine harness. They disconnected the 4 fuel and 4 coolant lines using the SAE J514 fittings, which required no tools. They then removed the propeller shaft coupling between the engine and the transmission, a single pin held by a cotter key. They removed the 6 engine mount bolts, 3 on each side of the hull, which had been designed with hex heads accepting a standard 1 1/8 inch socket. They attached the M32's boom hook to the 4 lifting eyes welded to the top of the engine cradle. The winch operator raised the boom, the cradle lifted clear of the hull, and the entire engine assembly came out as a single unit. The damaged engine was placed on the flatbed. The replacement engine, already inspected and tested at the depot, was hoisted into position by the M32, lowered into the hull, and bolted down. The connections were made in reverse order. The cooling system was refilled. The starter was engaged. The engine ran. Total elapsed time in a successful operation was between 4 and 6 hours, depending on conditions and crew experience. The same swap on a Panther was a 2.5-day operation requiring depot facilities, multiple specialist mechanics, and considerable hand-fitting of replaced components. The operational consequence of this maintenance disparity was, by every measure that historians have applied to it since the war, decisive. American Sherman units in the European theater achieved operational readiness rates that consistently exceeded 80% and frequently exceeded 90%. German Panther units in the same theater at the same time achieved operational readiness rates that hovered between 35 and 50%. The difference was not because American Shermans broke down less often. They broke down at approximately the same rate as Panthers, and they were destroyed in combat more often because they were less heavily armored. The difference was that when a Sherman broke down or was hit, it was back in service within days. When a Panther broke down or was hit, it was out of service for weeks, if it ever came back at all. The cumulative effect of this disparity over the 11 months between D-Day and VE Day was that the American armored forces were able to maintain combat strength at levels the German armored forces could not approach. A Sherman battalion that started a campaign with 60 tanks would still have approximately 48 to 55 operational tanks 2 months later, with a constant cycle of damaged tanks moving back to depots and repaired tanks moving forward to replace them.
A Panther battalion that started a campaign with 60 Panthers would have within 2 months between 15 and 20 operational tanks. The other 40 had been destroyed, abandoned, or were sitting in repair queues that never cleared. The American battalions kept fighting. The German battalions ran out of tanks.
Back at the field outside Saint-Manvieu-Norry on July 8, 1944 at 10 in the morning, Sergeant Earl Thornton climbs back into the driver's hatch of Carolina Belle. The new Ford GAA in the engine bay starts on the first crank. The exhaust note is the same throaty bellow he remembered from the engine that was destroyed yesterday. The tank moves out of the field, joins a road march heading east toward the front, and rejoins the 67th Armored Regiment by the early afternoon. The men of the 17th Ordnance Battalion who replace the engine clean their tools, load the damaged engine onto the flatbed for return to depot, and head to their next assignment, which is a Sherman with a damaged transmission 6 kilometers north. The whole operation, from the moment Carolina Belle was hit until the moment she rejoined combat, has taken less than 24 hours. This is the routine. This is what American armored maintenance looks like in Normandy in July of 1944. It is not heroic. It is not dramatic. The men involved are not famous, will never be photographed for the magazines, will not appear in any post-war documentary about the Battle of Normandy. What they have done is unspectacular. What they have done is invisible in the way that successful infrastructure is always invisible. But what they have done is win the war. Multiplied across thousands of Sherman tanks, across hundreds of ordnance battalions, across 11 months of combat in Europe, the routine ordinary work of replacing damaged engines and getting tanks back into the fight is the activity that keeps the American armored force in being, while the German armored force disintegrates. After the war ended, German tank engineers and tank officers who had survived the conflict produced a series of technical assessments of Allied armored vehicles for various Allied military intelligence agencies. Many of these documents are now declassified. Almost without exception, the German technical reports identify the same single feature of the Sherman as its most consequential design element. Not its gun, which the Germans regarded as adequate but unspectacular, not its armor, which the Germans regarded as insufficient, not its mobility, which the Germans regarded as good but no better than the Panthers. The feature German engineers consistently identified as decisive was its maintainability. The American tank, the German reports said over and over again, had been designed to be repaired in the field by ordinary mechanics using ordinary tools, and this design philosophy had given the American armored forces an operational tempo that no German equivalent could approach. General Heinz Guderian, the Inspector General of Armored Forces, wrote in his post-war memoirs that the rapid maintenance turnaround of American Shermans had been one of the most important factors in the campaign in the West. He noted that German panzer commanders had consistently underestimated the American capability for sustained operations because they had been calibrating their estimates against German operational tempo. When the Americans kept fighting day after day with units that should, by German calculations, have been combat ineffective from mechanical attrition alone, the German commanders did not understand what was happening. They eventually figured it out. By the time they figured it out, the war was nearly over. A complete Sherman engine power pack swap, in field conditions, by a competent Ordnance Battalion crew with appropriate equipment took between 4 and 8 hours. A complete Panther engine swap, in field conditions, took between 2 and 3 working days for a German maintenance crew with appropriate equipment, when appropriate equipment was available, which it often was not. A complete Sherman engine overhaul at a depot took approximately 3 days. A complete Panther engine overhaul at the Augsburg factory before it was destroyed in 1944 took approximately 3 weeks. After Augsburg was destroyed, complete Panther engine overhauls effectively stopped happening because there was no facility capable of performing them at scale. American ordnance battalions during the European campaign performed an estimated 11,000 engine swaps on Sherman tanks between June 1944 and May 1945. German maintenance units performed an estimated 1,900 engine swaps on Panther tanks during the same period. The ratio is not just 5-to-1 in absolute terms, it is more than 10-to-1 when adjusted for the relative number of tanks in service on each side. The American maintenance system was, in pure throughput terms, more than an order of magnitude more productive than the German system. And every one of those engine swaps put a tank back into combat that had been, until the swap, out of the fight. The power pack concept that the American Ordnance Department developed during the war did not disappear at the end of the war. It became the foundation of every post-war American tank design, and eventually of every modern Western tank design. The M26 Pershing inherited the Sherman's power pack philosophy. The M46 Patton, the M47, the M48, and the M60 all carried power packs derived directly from the Sherman lineage. The M1 Abrams, when it entered service in 1980, used a power pack with the AGT 1500 turbine engine that could be removed and replaced as a single unit, the same way the Sherman's Ford GAA had been removed and replaced 35 years earlier. The interfaces had become more sophisticated. The basic design philosophy was unchanged. European post-war tanks followed the same path. The British Centurion, designed during the war but produced afterwards, used a power pack approach. The German Leopard 1 and Leopard 2, designed in the 1950s and 1960s respectively, used power pack approaches that the wartime Maybach HL-230 had conspicuously lacked. The French AMX-30, the Israeli Merkava, the Russian T-90, the Chinese Type 99, all of them descend in their basic maintenance architecture from the Sherman's example. The lesson of 1944, that a tank that could be repaired in the field would defeat a tank that had to be repaired in a factory, was absorbed by every tank-designing nation in the world and was never forgotten. The Ordnance Department mechanics who actually performed the engine swaps that kept the Sherman force operational do not appear in many history books. They are not in the famous photographs of Patton or of Eisenhower or of the tank crews riding into liberated Paris. They were enlisted men, mostly, drawn from the ranks of American auto mechanics and farm mechanics and machine shop workers who had been drafted into the Army after Pearl Harbor and assigned to maintenance battalions based on their civilian skills. They wore standard olive-drab fatigues. They carried rifles like every other American soldier. They lived in the same tents and ate the same rations and took the same casualties as the combat troops they supported. But their work was different. Their work was repetitive, technical, methodical, and absolutely indispensable. Without them, the Sherman force would not have existed in the form that history remembers. Without them, the tank that won the campaign would have been simply another medium tank with limitations of gun and armor. There are no books written about specific ordnance maintenance battalions in the way there are books about specific infantry regiments or specific armored divisions. There are no famous battles named after ordnance units. The 17th Ordnance Battalion is not commemorated at any battlefield park. But the work the 17th Ordnance Battalion and units like it did every day throughout the European campaign was the work that made the campaign winnable. They are, in the truest sense, the unrecognized infrastructure of the Allied victory. The operational consequence of the maintenance gap, summed across the entire European campaign, can be stated in a single arithmetical fact. By VE Day, the American Army had fielded more than 50,000 Sherman tanks in the European theater. The number of combat-ready Shermans available to American armored units on VE Day was approximately 12,000. The number that had been destroyed beyond repair during the campaign was approximately 7,000. The remaining 31,000 were tanks that had been damaged at some point during the campaign and then returned to combat readiness through the maintenance system. Every one of those 31,000 tanks represented a combat capability that the maintenance system had restored, sometimes once, sometimes multiple times. Many Shermans had 3 or 4 different engines over their service lives. Some had 5. By contrast, German Panther production during the war totaled approximately 6,000 vehicles. Total operational Panthers available to the Wehrmacht at any given moment during the European campaign never exceeded 800, and most of the time was well below 500. The gap was not just in production, it was in operational availability. The Americans made more tanks than the Germans. They also kept the ones they had running. The Germans did not, because they could not. In a war decided by what worked was the power pack, the engine that bolted out in 6 hours, the cradle that made it to any hull, the quick disconnect coupling that sealed itself when broken, the M32 with its boom and winch, the ordnance battalion in its tent next to the wheat field, the depot in Liège processing engines around the clock, the crated Ford GAA on the flatbed, painted olive drab, stenciled with white block letters, ready to drop into whatever Sherman needed one. The German mechanic standing in the Norman farmyard in July of 1944, looking at the captured Sherman with its rear deck open and its power pack visible, understood what he was looking at and understood that his army had not built this and was not going to build this. He wrote his report. The report was filed. The Panther continued to be assembled in dwindling numbers with its individually threaded fuel lines and its hand-routed wiring harness and its non-standard engine mounting points until the factory at Augsburg was bombed and the production line stopped. The Sherman continued to be produced and repaired and re-engined and returned to combat in numbers that the Wehrmacht could not match and could not even meaningfully reduce. In a war fought between industries, the tank that could be repaired in the field was the tank that won the campaign, not because it was a better tank in any individual engagement, which it was not, but because it kept showing up. Day after day, week after week, month after month, the American armored battalions kept fielding combat-effective tank companies through a process that nobody outside the Ordnance Department fully understood and that nobody in the post-war popular history has ever properly explained. The mechanics did the work, the engines came out, the new engines went in, the tanks rolled forward, the campaign was won. The German engineers who studied the captured Shermans understood what they were seeing. By the time they understood it, it was already too late. The system had been built. The system was working. The system kept working until Berlin fell. That is the story of the tank that everybody knows and the system that nobody knows. The tank is famous. The system is not. But the system is what put the famous tank back into the fight every time after every hit for the entire length of the war. In a war decided by what worked, the system worked. The German mechanics, looking at it for the first time in the summer of 1944, knew they were looking at something their army had not built. They were correct. They were also looking at the reason their army was going to lose.